We're now going to go to the meat of the course, where, of course, Calculus 2 is mainly about integration. And of course, not all functions are going to be easy, right? You're not all going to be like, polynomials, exponential functions, uh, just sines and cosines by themselves. Those things that we have easy backward formulas from Calculus 1, right? From those easy derivative formulas. We have to learn how to integrate some complicated things. We've already seen some of that with U substitution. Now we're going to go ahead and attack another class of integral using probably one of my favorite techniques. I've called this in the older videos, the granddaddy technique, integration by part. And to motivate this, we're kind of going to start a little silly here, small deviation from what we usually do. Now, the main thing that we're going to be focusing on throughout this next part of the course is, well, technique, technique, technique. Okay, technique. Well, what is it? See, in Calculus 1, when we learned differentiation, right? We learned all the basic stuff, the power rule, the product rule, the quotient rule, the chain rule, all those basic patterns for sine, cosine, exponential, arcsine, implicit differentiation, whatever. And, you do some stuff, do some algebra magic, and you're done. Integration, on the other hand, well, it's not so straightforward. You can apply a use substitution. You may not be done. You got to do some other stuff. Okay. Integration by parts will be the technique that we'll learn here. We'll also learn about partial fractions. Some of you, yeah, that will take Calculus 3 will know Stokes theorem. Uh, and of course, Bessel functions. And that's a special functions thing that shows up in differential equations, some engineering things. But the point is, integration is its own complicated mess. And if all else fails, you probably might want to burn the evidence and start over. So, what is integration by parts? Okay, and this other comic from XKCD does kind of sum up a little bit. So you have an integral to form. Okay, you're integrating f of x, g of x, dx. So you have a product, and you're going to select some variables so that u is say f, and this dv, or rather v, is such that dv is g of x dx. You could frame this a slightly different way. Okay, sometimes it's framed with g prime dx, but same thing. And now the original expression becomes the integral of u dv. And the video's over. No, no, I'm not going to leave it. But I want to take some time to actually develop where this integration by parts formula comes from. And we're going to use this classical, the standard notation that we see, this UDV, and we can relate it to F and G. Okay. So let's go ahead and demonstrate where the formula comes from. And I want to go back to one of the basic things that we learned from Calculus 1, product rule. See, whenever we have a differentiation rule, there's some stuff. There's always an inverse integration rule. Okay, for chain rule, for example, we learned that's U substitution. It's just a chain rule. Okay, what we'll see is that the product rule is that for integration by parts doesn't. Okay, so how do we do this? Well, let's start. Okay, the IBP formula, and I definitely can't spell. So let's develop the IBP formula. Let's first start with, say, the differential of U times V. Okay. So think about this as U and V are functions of X. So interpret this as, say, U is a function of X, V is a function of X. Okay. And so we're just going to use the product rule here. So first times the derivative of the second. So first times the derivative of the second. So U times the derivative of V, which we'll just write the differential here, dV. Okay, now plus, okay, second times the derivative of the first, V du. Okay, you can interpret this again with the usual primes and stuff. And now what I'm going to do is integrate both sides of this equation, okay? So when I integrate, I'm integrating d of uv is equal to the integral of u dv plus the integral of v du. Okay, and on the left there, I'm integrating this differential, this derivative. Okay, it's looking a little funkier than some stuff that we've seen before. You can phrase it if you want. It's still just integral. We're not going to get into that. But the thing here is that the integral and the differential will cancel each other out. Again, FTC. So we'll have uv equals the integral of u dv plus the integral of v du. And I want to go ahead and subtract that second integral over and do some shuffling. And what we'll have here is that the integral of u dv is equal to uv minus the integral of v. And this, folks, is our integration by parts formula, which comes from the product rule. Okay, I just wanted to take some time to show where that comes from. And the idea here, okay, is that we want to choose u such that it has an easy derivative, so to say, and v, which has an easy integral. Okay, so u has an easy derivative, I can spell, don't worry. And then dv is the easy integral. Now, of course, if you have a definite integral, okay, you just plug in the points in the boundary, right? Integrate from a to b, you get the same usual. Okay. Now, before we go on to some actual examples, I want to mention this so-called Liotte heuristic, which tells us how to select u and dv. Okay, I'll just go over this real quick, and we'll come back to it, okay, when we need it. So, Liotte, okay. Let's keep, let's do it here on the side. The Liotte is a heuristic. It's not an absolute rule that tells us how to select u and dv. So the L stands for logs, I for inverse functions like arctan, okay, or even logs fall under that. A for algebraic functions, so monomials, square roots, okay. T for the trig functions, sines and cosines, for example, and then E for exponential. Okay. And now what we do here is that whatever uh, shows up at the top of the hierarchy, okay, so whatever comes up at the top here is probably going to be your more clever choice of u. Okay. Whereas going from the bottom up is probably an idea what you should choose dv. Okay. Some people may also frame this as detail. Okay. Detail, DETIL. Okay. The D meaning dv. Okay. And we'll see how this comes into play. Okay. So enough talk. Let's just get to some examples here. Let's see how we can transform problems like this into problems like this. So we have our first problem here. And in fact, what I'll do here, just to keep this handy, I'll go ahead and select our integration by parts formula here. That way we have it ready to go. Okay, copy that. All right, and we're going to look at this integral here. The integral, okay, we're going to integrate x squared, x times e to the 2x dx. Okay. Well, let's again think about our little Liotte heuristic. Okay, I'll go ahead and scroll back up real quick to that. So Liotte says, I may want to choose u, okay, from the top down here. And in that integrand, x times e to the 2x, I have x, which is an algebraic function. That's a monomial. Okay, it's a polynomial type thing. And it's the easier thing to differentiate. But Sean, you say, e to the x is easy to differentiate as well. Yeah, but polynomials are easy. They're easier. So we're going to go ahead and do our variable declarations. Okay, we're going to go ahead and follow our pattern up there. Okay. So here's what we're going to do. We're going to set u equal to x and dv equal to e to the 2x dx. Okay. And now we're going to go ahead and fill in the rest of this table. Okay. Notice the colors I'm using. Birds up, right? Okay. So we're going to go ahead and fill in the rest of this table. So we're going to need a v. We're going to need a du. So now going from u to du, that's a derivative. And going from dv to v, that's an integral. Okay. So when u equals x, du is, okay, think back to when we did u substitution, right? Du is equal to 1 dx. Okay, and then when I have dv equals e to the 2x dx, I integrate that, okay? Remember how we integrate exponentials, right? So let's go ahead and write that up here as well, okay? Integrating e to the kx dx 1 over k e to the kx plus a constant. Okay, we divide by that exponent, the scale factor of the x. Now, of course, when we do the integration here, we're going to ignore the plus c here. It won't matter in the end. So v here is just going to be 1/2 e to the 2x. And now I'm going to go ahead and follow my path here. U, v, minus the integral of v to u. Okay, so let's go ahead and write down what we have here. So the integral of x e to the 2x dx is equal to u times v. So I have 1/2 x e to the 2x minus the integral of v du. So v, well, let's see here, v 1/2 e to the 2x du is dx. And now I have an integral that is much easier to work with, okay? This 1/2 e to the 2x thing, easy, because I can just use the orange thing in the corner there, whichever corner it is. Let's think about it. Up there somewhere. Yeah. Okay. We're going to use that same rule there, okay? So the first term stays the same. And then we'll have a minus, okay? Well, we can pull the 1/2, and I'm going to divide by another 2. We'll get a 1/4 e to 2x plus a constant. That's how we use integration by parts. Right before, if you would have gotten this, you would probably be trying some u substitutions and maybe doing some illegal things here, but this is bringing up a good point here, okay? Whenever we integrate a product of functions, just like with the product rule of differentiation, you don't integrate pointwise. I'll say that again. The integral of a product is not the product of an integral, just like the derivative of a product is not the product of derivatives. That's why we have integration by parts here. Right. Go ahead and do some more examples, right? I got another one here, x squared cosine 3x, okay? Now here in this one, again, I have an algebraic function, a polynomial, x squared, against a trig function. So usually 9 times out of 10, whenever you see a polynomial, you may want to make that your u. So we'll have u equals x squared, and then dv equals cosine of 3x dx. Okay, we fill in the rest of our table. So du, we take a derivative. Du is 2x dx. And then v, we integrate, okay? The antiderivative of cosine is sine. And then think about the u substitution here. Okay, when you do this, right, this linear function compose inside, just dividing by the slope. You need to compensate by dividing by a 3. 1/3 sine. Okay, and now follow the path. U, v, minus the integral of v to u. Okay, so this integral, let's write it. Let's start again. X squared cosine 3x dx is equal to, all right, u times v. 1/3 x squared sine 3x. Okay, it's a little more customary to put the polynomial stuff in front of the trig. Okay, same for exponentials. Okay, minus the integral of v du. Let's go ahead and push some of those constants out. So we have a 2 and a 1/3 there. Those smash together to a 2/3. So we'll have 2/3 times the integral of x sine 3x dx. Just give up here? No, we can just use integration by parts again, right? Okay, you can use integration by parts again, okay? So that's what we'll do here. We'll have a second choice for integration by parts. And whenever you do multiple integrations by parts, okay, whenever you do parts multiple times in the same problem, you want to make your choices similar, okay? Because notice if I selected u equals sine 3x here, I'd actually be going backwards and I wouldn't be making any forward progress. Okay, for you chess players, it's like moving your rook from a1 then to a2 then back to a1. You haven't done anything. So let's go ahead and set up our table again. So in this one, we'll have u equals x, okay? dv is equal to sine 3x dx. And this is now where some of the signs, SIG and S, come into play here. du is dx. And v is equal to, there's the 1/3 there still because of the chain rule, right? Ah, but the antiderivative of sine is negative cosine. Very careful with that. Follow your path. And now, this is where we're going to have to be a little careful here. We write our first stuff down. Now, minus 2/3. Now, we're integrating this next part here. Whoops. Integrating this chunk here by parts. So that's why I wrote the parentheses down, okay? So 2/3 times that integral. But now we're going to use the parts formula. So u times v. So x times negative 1/3 cosine 3x. And then minus the integral of v du. Okay, be very careful here. Minus times a minus 1/3. Minus is plus, okay? I'm going to go ahead and write this in just like this. Remember, the integration by parts formula has a minus sign built into it, okay? Be very careful with those minus signs. Okay, we can actually go ahead and do some cleaning up here. So x squared sine 3x. Now I'll distribute the 2/3 in, so we multiply 2 over 9x cosine x. Okay, and then I'll have a, well, this is where stuff gets a little hairy, okay? Minus on the inside there, that's a plus. Then there's another minus, so that's a net minus 2 over 9. Okay, integrating cosine of 3x dx. And we've already done this before. You see it in the first bit of orange there. All this stuff stays the same. 2 over 9x cosine 3x. Okay, and then we're going to divide by 3 again, so 2 over 27 sine of 3x. Plus a constant. Sometimes you might have to integrate by parts multiple times, okay? Key thing here is to keep track of those minus signs, okay? Remember that the minus sign is built into the integration by parts formula. Very careful with that. Okay. Now, if you're ever unsure on your answer, you can always take derivative and see what happens. It'll be an exercise in combining like terms, but I think it's good. Now, this one looks funky. Theta, sine theta, cosine theta, d theta. There's probably a number of ways you can tackle this, okay? There are probably a number of ways you can tackle this. Okay? You can set u to be theta, dv to be sine theta, cosine theta, d theta, and then there's a clever way, okay? In fact, let's go ahead and go with that natural choice here, okay? Because something nice will come out, and this will show you how some of these integration techniques will work in tandem. So I'm going to set u to be theta, so that du is d theta. And then dv will be sine of theta, cosine of theta, d theta. Sean, why did you do that? Let's check this out. Let's go off to the side here, okay? Because when I want to integrate this guy, I see a function and its derivative. Derivative of sine is cosine. Hey, do a u sub, right? Okay, but I'm going to go ahead and call it something else here. W equals sine theta. So dw is cosine of theta d theta. Now take a look at what I got here. This guy right here is just 1/2 w squared, right? Plus a constant. It's just 1/2 sine squared theta. One way to approach it. Okay, so v here will be 1/2 sine squared theta. Again, just showing you how those integration techniques work in tandem. Follow your path. So the integral of theta, sine theta, cosine theta, d theta. Okay, with this choice here, we'll have 1/2 theta sine squared theta minus the integral of v du. Uh-oh, something's funny here. 1/2 times the integral of sine squared theta. At the moment, okay, we don't have a nice formula for this, but we can remember something here, okay? We can use the fact here, I'll put this in, say, this light blue here. we can use the fact that sine square of theta can be rewritten as 1 minus cosine 2 theta over 2. Okay? This is a formula that we'll have and we'll need from time to time. Okay, this one, okay, shows up a lot. Let's go ahead and finish this out here. I want to go ahead and lead us to the end here. So we'll go ahead and rewrite our integrand here. So it'll be 1/2 times 1 minus cosine 2 theta. Theta. Okay, now some of the magic will happen here. 1/2 theta sine squared theta stays the same here. Okay, half times a half is a fourth. Tribute, that's just a 1/4 in the integral. 1/4 theta. Now for the other one, 1/2 cosine 2 theta. All right, we'll have to do a division by 2. Well, actually, let's just go ahead and see that. Let's look at that. 1/4 cosine 2 theta. Theta. Okay, antiderivative of cosine is sine, but then I need to divide by a 2 because of that chain rule. So all this first stuff stays the same. And we'll have plus 1/8, not cosine, but sine 2 theta plus a constant. So that's one way to approach this. Okay. This is a bit funky because it requires you to remember this formula here. Hey, let me actually fix this here. There is another way to approach this, okay? An alternate solution, okay? You can recall that sine of 2 theta is equal to 2 sine theta cosine theta. And so that means sine theta cosine theta is 1/2 of sine 2 theta. And in fact, integrating theta against sine 2 theta, well, I've done something like that here already. Multiple ways to attack an integral. Okay, I'll leave that solution for you. See if you can figure it out at home. Here's a fun one. T squared log t. Okay, t squared log t. Okay, t squared log t. Well, let's go back to our little Lyautey heuristic here, which I'll go ahead and copy. So, lasso. So we have t squared log t. I want to figure out what to choose for my u and what to choose for my dv. Okay. Question is, well, what do I choose here? Well, I have a log there that's at the top of the hierarchy, L, log. That's going to be my u. That's easy to differentiate. Yeah, you'll see. Gotta have the pointy end down, right? Set u equal to log t here. Okay, so dv is the rest. T squared dt. Fill in the rest of the table, right? du is equal to 1/t dt. And v is equal to not 2t, but 1/3 t cubed. Sean, I think you made this harder. Just, just roll with it. Roll with it. Follow your path. T squared log t, an integral. U times v, so we'll have 1/3 t cubed log of t minus the integral of v to u. 1/3 times 1/t times t cubed dt. Okay. T cubed over t. Wait a minute. Dividing with exponents, subtract the powers. That's just t squared in there, isn't it? You betcha. We'll have 1/3 t cubed log t, the outside there, minus the integral. So minus 1/3 this integral, t squared dt. Now that's easy. 1/3 t cubed log t minus, okay, think about the power rule. Add 1 to the exponent, divide by the new exponent. You get t cubed over 9. plus a constant. Pretty funky, huh? Right here, we chose u to be the log function because something nice happened to me. I'll pose a challenge here. Find a pattern. Okay, there's a nice pattern here. Find a pattern for any n here, the integral of t to the n log t dt. Try this with the n equals 3 case next, because we did the n equals 2 case. Try this with the n equals 3 case, and n equals 4, and see if you can find a pattern. I'll leave that for you. That's a nice little fun thing. Ah, this is a favorite one of mine. E to the 2x sine 3x dx. All right, so based on our little Lyautey heuristic, which I'll paste back here, right? Okay. Well, I got a trig function there, sine, and an exponential. They're both relatively easy. Excuse me. Just to follow the heuristic, and it actually won't matter which one you choose in the end. You'll kind of see why. Whoops, that's not what I want to do. Okay. We're going to go ahead and start out by doing this, okay? We're going to start out by saying, okay, just by following the heuristic here, let's let u be sine of 3x and dv be e to the 2x dx. Okay, now we fill in the rest of the table. Derivative of sine 3x, that's 3 cosine of 3x dx. And then our v is 1/2 2x. Okay, again, when we integrate an linear and exponential composed with a linear, or I should say exponential after linear, I should say, where the exponent is a linear function, we divide by the slope. Okay, do u sub, you'll see it. Okay, follow our path. And now we're going to watch the magic unfold here. I'm going to write down my original integral, e to the 2x, not, there we go, sine of 3x. The x is equal to, okay, so now we do this thing, uv, so we've passed our derivative through, 1/2 e to the 2x sine 3x minus the integral of v to u. I'll pull out all the constants here, 3/2 times the integral of e to the 2x cosine of 3x. All right. Well, the resulting integral looks similar to the one that we started with. Okay. So we're going to go ahead and make a similar choice here. Once again, set u to be the trig function, cosine. And so dv is going to be, once again, e to the 2x, okay, dx, which means v is 1/2 e to the 2x. And du is, let's see, negative, careful, negative 3 sine of 3x. dx. Follow your path. And watch the magic. Okay. A bit of sleight of hand here. Actually, let me go ahead and move this stuff here. I'm gonna need a bit more room. So 1/2 e to 2x sine 3x minus 3/2, and now this is gonna be the new integral, okay? U times v once again. It's gonna be another 1/2 that comes out. E to the 2x cosine of 3x minus the integral of v to u. Well, I have a 3/2, but there's a minus. But my integration by parts formula has a minus built in, and minus times minus is plus. Plus 3/2 times the integral of e to the 2x sine of 3x dx. That just put me back to where I started. Did I do something wrong? No. That's the punchline, okay? Remember that sine and cosine have this cyclic pattern of derivatives. So this is to be expected. The cool thing is, our unknown integrand, our unknown function, right? We don't know how to integrate this guy. That's right here. It showed up again. So how do we handle this? We're going to go ahead and give this a name because now what we do have is one equation in the unknown integral. Call this integral I, okay? We're going to call this thing I, okay, or J. Capital I is usually what we use here. So we're going to go ahead and set I equal to this thing. So I, rewriting the equation, we have I equals 1/2 e to the 2x sine of 3x minus 3 over 2 times 1/2 e to the 2x cosine of 3x plus 3 over 2 I. Okay, just keeping the colors there so we can all see. Solve for I. All you got to do is solve for capital I. Okay, so we're going to go ahead and do some cleaning up, some simplification. Okay, and then we'll solve for I here. So distributing on the left here, on the right, excuse me. Okay, first stuff stays the same. You get a minus 3 over 4 here. And then 3 times 3 is 9, okay, over 4. All right, now I'm going to do some magic here. I'm going to add 9 over 4i to both sides. Let's console that in there. Add 9 over 4i. 1 plus 9 over 4. Okay. Well, 1 is 4 over 4. Okay, 4 plus 9 is 13, so 13 over 9i is now equal to, I really don't want to write this again. Okay. Power of technology, right? Copy, paste. And now how do I solve for I? Well, let's multiply by 9 over 13. So the integral that we want, which remember was e to the 2x sine of 3x. The x. Okay, we're going to multiply by 9 over 13 of all that stuff here. So let's write it in. Actually, let's not. Okay. Thankfully, I have a copy already. Mathematicians are lazy. Don't judge me. And of course, we're going to have our plus c there because it's an indefinite integral. And we can just go ahead and clean up here. So 9 over, actually, being lazy once again. Oop. So the coefficient on the sine part here, okay. 9 over 13 times 1/2, that's 9 over 26. On the cosine part, 9 times 3 is 27. Over 13 times 4, 52. Plus a constant. So this demonstrates what you need to do if you're integrating, say, an exponential against a sine or a cosine, okay? I encourage you to work out the similar looking integral where the sine here is replaced with a cosine. Okay, you'll get into a similar pattern here where you're going to run into this cycle, this loop here. You have to solve for the unknown integral. So the challenge here that I'll also pose for you, okay, so the challenge is to do the same for this integral I'm calling j. But once again, we're replacing sine, cosine. Okay, do the same, and you should get something that looks similar to this. All right, very good. Now we're on to a definite integral, okay? Integrating t against e to the minus t, this time on 0 to 1. Okay, and we're remembering our Lyautey heuristic. Easier here is to let u be the polynomial, okay? U equals t. All right. Dv e to the minus t, t. Now we fill in the rest of the table, okay? du equals dt. b equals minus e to the minus t, okay? Be very careful. Oops, that's in the wrong color. Not to worry. Select rectangle. Now it's in the correct, well, mostly. Okay. Anyway, punchline is follow our path. And now when we do a definite integral, okay, whenever we do integration by parts, okay, we're going to have an extra bit here to do, and that's to evaluate on the boundary, okay? This reduces this to an evaluation on the boundary and then integrating another sort of derivative. We're passing derivative through. Okay, so u times v is negative t e to the minus t on the boundary, then minus the integral of v to u. Okay, minus times minus is plus, and it's still an integral from 0 to 1. Okay, so notice here that the only change I made is that whenever I have a definite integral, I evaluate the product term, that uv, on the boundary, okay, at the endpoint. Top minus bottom there, usual FTC stuff. And then the new integral is again still with those same limits. Okay, now let's go ahead and do some of the work here. And I'll actually go ahead and just do the second integral just so we can do all the evaluations at once. So I'll have minus t e to the minus t. And then, of course, antiderivative of e to the minus t is minus e to the minus t. Evaluate all this between 1 and 0. Let me give myself a bit more room here. Okay, power of technology or not. So here. Okay, but nonetheless, we're going to go ahead and evaluate this all on the boundary. So between 1 and 0. Okay. Now be careful here. E to the 0 is not 0. E to the 0 is 1. So let's go ahead and write down exactly what we'd be typing into our calculators. Okay. We have negative 1 times e to the minus 1 minus e to the minus 1. Okay. Minus, okay, negative 0 times e to the negative 0 minus e to the minus 0. Okay, so we have, let's see, negative e to the minus 1 minus e to the minus 1. Well, negative 1 minus 1 is negative 2. Okay, those are like terms. Well, 0 times anything is 0. Okay, minus minus is plus, and e to the 0 is 1. Our final answer is 1 minus 2e to the minus 1. Okay, that's how we do that one. All right. Now, we're at this point in the video where I think hopefully you've gotten the hang of this, what I'll call the classical formulation of integration by parts. U v minus the integral of v to u, blah. In some ways, there's a shorthand, okay, that you can use to cut down on the amount of stuff that you write. And that's the so-called DI method. I'm sort of abridging this a little. You also see this called as the table method, tabular method of integration, also known as the stand and deliver method. For those of you that haven't seen Stand and Deliver, by far one of my favorite math movies of all time. But let's go ahead and demonstrate this with a shorthand, okay? So we're going to go ahead and set up two columns here. I have a D column and an I column, okay? The D column will correspond to my choices of U, and my I column will correspond to my choices of dv. So here I chose u to be t and dv to be e to the minus t. Well, dt, but I'm going to go ahead and leave off the differential here. Now what I'm going to do is I'm going to differentiate in the d column until that thing vanishes, until the derivative is 0. So the derivative of t is 1, and the derivative of 1 is 0. So now my derivative has vanished. I'm now going to integrate as many times as I differentiated. Okay, so we have minus e to the minus t, and when I divide by another minus 1, I get a plus sign in front of it, so I get that. Now here's where we're going to get a little funky here, okay? In green, okay? Starting from the top of the D column here, we're gonna put a plus sign. We're gonna alternate signs until we get to the end. Plus, minus, plus. If you have more rows, plus, minus, okay? Those are factors in front. Okay, you'll see how they correspond. And then we build these shoelaces, okay? Or as Jaime Escalante says in the movie, okay? Edward James Olmos, okay? Played by Edward James Olmos, okay? Tick, tack, toe. What I've just joined there with those magenta shoelaces, those are a product. So you join the first thing in the D column, the second thing in the I column, second thing in the D column to the third thing in the I column, and do that until you run out of pairs. Well, obviously, when you get to the 0, there's something else going to be. And then you're just going to read it off, multiply things joined by a shoelace, okay, and give it the corresponding sign in front. So think about this as multiplying by a +1, a -1, a +1, and so on. And so what do I have here? Take a look. T e to the minus t with a minus sign. -1 times +1 is -1. Okay? Now, minus e to the minus t. I'm evaluating this between 1 and 0. I got the same thing, right? Check it out. This thing here is exactly this thing here. Pretty neat, huh? I'll warn you, for the DI method, okay, use this as a shorthand when you're integrating a polynomial, okay, against a sine, cosine, or an exponential, okay? You can kind of use it to help you organize your integration by parts, okay? But this DI method, okay, I'll put this here. Okay, whoops, that's the highlighter. I don't want that. Okay. DI works best. I can spell when integrating a polynomial, which you'll choose your polynomial to be u, okay, against sine, cosine, or exponential. Okay, that way the derivatives will vanish there on the left-hand column, and then you'll have everything you need. And it's a shorthand. Okay? Notice how I said short. I didn't say shortcut. I said shorthand. You still know the classical formulation, because sometimes the DI method will not get you where you need to be in the promised land, as we'll demonstrate here. It's that funky arc cosine function again, but this time we're integrating it. We're not differentiating it. Actually, we're going to be differentiating it. 0 to 1/2, okay, arc cosine x dx, okay? Remember that arc cosine, this inverse cosine function, remember that -1 is not an exponent, just old notation for inverse function. That's the function whose cosine is the number x in there, okay? Well, how do we handle this? Well, anytime I'm integrating these inverse functions, okay, let's bring back Liate here, our nice friend here. Let's bring them back here, okay? Copy and paste, right? Right, bring that back. How's it going, friend? All right. Whoops, that's not what I wanted to click on. I clicked on my OBS setup on accident. Okay, that's not good. Oh boy. Okay, there we go. We're still recording. All right. So notice how I said at the beginning, right? I for inverse. What does that really mean? Well, this is an example of an inverse function, right? Arc cosine of x. So that's at the top of the hierarchy. We'll have u be the inverse cosine. Sean, there's nothing else. Yeah, there is. There's an invisible one. You gotta remember that sometimes. So let's go ahead and do this. So let u equal arc cosine x, and let dv be just 1 dx, okay? Let's actually make that a little more explicit there, 1 dx. So v is equal to x, and now du is equal to, well, I'll be honest, okay? I'm usually one that forgets how to work with arc sine and arc cosine with their derivatives, and then okay, how to integrate those funky things. We'll learn how to handle those in a future section. But here's how I always like to reverse engineer the derivative of arc cosine, okay? Of course, work with your tables, right? If you have a derivative table, you can easily look this up. But here's how I always like to reverse engineer it. Okay, let's do this light blue. Okay, if I want the derivative of arc cosine x, this is a little calc 1 refresher on implicit differentiation. If you just want to skip ahead, right, just go ahead and skip ahead to future timestamp, okay? So I'll invert, I'll take the cosine on both sides. We'll get cosine of y equals x, okay? And now I'm going to take the derivative okay, with respect to x on both sides. Okay. Two things are equal, so derivatives are equal almost everywhere. All right, well, on the right, I just have 1. But on the left, well, you gotta remember, right? Taking the derivative of something that has another function in it, chain rule, right? Derivative of cosine is negative sine, and then times dy dx because of the chain rule. Now we solve for dy dx, so dy dx is equal to, okay, this thing that's going to be up soon. Okay, so dy dx is going to be equal to minus 1 over sine y. But I want this in terms of x. Remember from here, right? X equals cosine of y. I'll remember how to do this soon, okay? Draw a triangle. Y is my angle. Okay, cosine is x, which is x over 1. Cosine is, what is it, folks? SOHCAHTOA, adjacent over hypotenuse. And the missing side can be found here by Pythagoras. Okay, I'll skip some of the details there. But what's 1 over, what's the sine of y here? Sine is opposite over hypotenuse. Square root 1 minus x squared. So this is minus 1 over x squared. And that's our derivative. Again, you can always look this up into a table when you practice, okay? But this is just a good way I like to reverse engineer it. So after all that nonsense, we get that du is minus, I'll write it like this, dx over square root 1 minus x squared. Okay. Follow your path. Let's write down the original thing here. Integral of arc cosine x dx. So u times v will have an x cosine inverse x, evaluated on the boundary, minus the integral of, okay, 0 to 1/2 of, well, remember, okay, minus times minus is plus, okay? That minus sign built in, minus x over square root 1 minus x squared dx. Move this over. There we go. Okay. All right, so now that second integral may look a little scary, okay? Whoops. That second integral may look a little scary, but that's fine. We can go ahead and attack that with a variable change, okay? I've already used u and v here. You can use whatever variable you want here. It's a little easy to see, like, if you think about doing these u substitutions more often, you'll be able to see the chain rule pop out. But let's go ahead and tackle this last integral here, okay? Let's just get the antiderivative here, and so that we can get the result that we need. Let's do this in gray. Probably not the best color. So we're doing this, x over square root 1 minus x squared. Okay, I'm going to set, say, y equal to, actually, I already used y. Let's use, say, z. Z is equal to x squared. All right, let's make it 1 minus x squared. And dz is equal to, well, just follow the same rules for u substitution, right? Minus 2x dx. You shuffle over, right? Minus 1/2 dz equal to x dx. So our integrand is transformed into 1/2 minus 1/2, okay, times, well, x dx is dz over square root of to z. We know how to handle that. That's just power rule, right? That's just z to the minus 1/2, okay, times, so minus 1/2 there, times z to the 1/2 divided by 1/2, we multiply by 2, plus a constant. So the antiderivative that we want there is minus square root 1 minus x squared after we back substitute, plus a constant. So let's go ahead and take that result there. Okay, lots to do here. X arc cosine x minus square root 1 minus x squared. Okay, evaluate on the boundary. Okay. Let's go ahead and write down what we would need. 1/2 arc cosine 1/2 minus 1 minus 1/2 squared. And then minus, well, get a 0 from the first term. Okay, 0 times whatever is 0. And then 0 squared is 1, 1 minus 0 is 1. Okay. But what's the arc cosine of 1/2? Remember, that's the angle whose cosine is 1/2. Okay, so think back to your unit circle. Okay, have it handy if you need to. The angle that we're looking for is pi over 3. Okay, check that. Cosine of pi over 3 is indeed 1/2. Okay, and then minus square root of 1 minus a fourth. We can keep cleaning that up a little. Pi over 6 minus 1 minus a fourth is 3/4. Okay, and then square root of 3 over 4, that's square root of 3 over the square root of 4. Simplifies to that square root of 3 over 2, and after all that, all right, so you see how powerful integration by parts is? See how nice this is? Okay. We had to do some side calculations here, but of course, you can always look up this derivative. You can always do this off to the side, but you can see how these integral techniques are being used in combination with each other. We've seen that a very long time, okay? All right. This one's a doozy. X to the 5th e to the x squared dx here. So how do we handle that? Might try a few things, okay? Now, remember for u substitution, right? Whenever you see the functions inside the functions, the innermost composition, that's going to be a clue that might be your u. But what about the rest? We're going to go ahead and transform this, okay, in a way here. Here's what we're going to do. We're going to write this integral, x to the 5th dx squared dx. I'm going to take away one of the x's, okay? We have x times x to the 4th e to the x squared dx. Sean, where are you going with this? Okay, or maybe some of you all saw the brilliant move, okay? Okay, this is going to be the brilliant move here. Okay, for you chess.com players there, this is the brilliant move here. The brilliant move here is to write x to the 4th as x squared squared. What? All right, let's walk through it, okay? Let's see how this works. So, if I'm going to do a variable substitution here. I'll start off by calling it, say, I don't know, w. W equals x squared. So dw is equal to 2x dx here, okay? Now I divide by 2, I get 1/2 dw equals x dx. And, oh my goodness, take a look at what I got there. This is brilliant, right? Okay, w is equal to x squared, x squared, x squared. Okay, and then my dx junk, right? Half dw is dx, x dx there, x dx. I can simplify everything now. Just take a look now what I got. I got 1/2 the integral of w, okay, w squared e to the w dw, okay? Note that the x dx is 1/2 dw. What does this look like now? Just parts again! What we just started with, okay? I'm going to go ahead and use DI method because this video is running a little too long here, okay? So we're going to go ahead and do our DI method here. Remember, 2 columns. D is going to be for your U column. I is your DV column. So we're going to set I equal to e to the w here. And then D is w squared. Okay, differentiate in the D column until it vanishes. 2w, 2, 0. Integrate as many times here. Thankfully, we're integrating e to the w, so that's easy. Okay, get your signs in order. Plus, minus, plus, minus. And now, tic-tac-toe. Okay, so what do we have here? I have 1/2 times first shoelace. You have a plus sign there. W squared e to the w. Second has a minus. Minus 2w e to the w. Okay? Third, 2. That's a plus 2 e to the w. Okay? Plus a constant. Now you back sub. Okay? W is x squared. So w squared, x squared is x to the fourth e to the x squared. Minus 2 x squared e to the x squared. Plus 2 e to the x squared. Plus constant. You see how slick that is? See how clever that is? We used a priming substitution to force integration by parts. And again, it's showing you that these integration techniques work together, work in tandem. All right. Very good here. Okay, that DI method is powerful again because we are integrating a polynomial against an exponential here. And then we just follow back. Follow back. Okay. Excellent. All right. So that's enough shenanigans out of the way for that one. Now here's another funny looking one. Log of square root x dx. And we're integrating from 1 to 4. Two ways to attack this. I would naturally attack this with a priming substitution. Okay. So priming substitution in that regard means it would be nice if I could get rid of that square root there, because then I can turn this into an integration by parts problem that looks manageable. Okay. In fact, we did an integral that looks like this with a log before. Okay. Go back. We integrated a t squared log t, and we have a pattern for this. We'll find a pattern for this, t to the n log t. And it turns out that we can reduce the problem that we have now. Okay, we can reduce this problem, log squared x dx, into an easier problem to know how to work with. So here's the priming substitution here. Here's the priming substitution. We're going to let y equal to, actually, we're going to do it like this. We're going to let x equal y squared. What? Why? Let me explain. When x is equal to y squared, okay, think about it. What's the square root of x? Square root of x is not zooming in. Square root of x is equal to the square root of y squared, which is, well, if we take principal parts, whatever, it's just y. Okay? So now take a look here. dx is equal to what? 2y dy. Okay? We're getting somewhere. But we still need new limits of integration, right? Whenever we change units, we got to change the limits of integration. Okay? So whenever, okay, I change my variables, okay, whenever I do a u sub or a y sub in this case, I need to change the limits of integration. But here I'm going from the x world to the y world, okay? So when x is equal to 1, okay, when x is equal to 1, what is y? Well, in this case, well, and you can also use the solve form there. When x is equal to 1, that means y is equal to 1. When x is equal to 4, okay, well, what number squared gives me 4? 2. And so now, take a look at what we got here, okay? We're going to do a priming substitution here. So let's write down what we have. This integral from 1 to 4 of log of square root of x dx. You could also cheese this if you remember one of the log power rules, but this is going to demonstrate something too, okay? So we're going to change variables, okay? So it's the integral from now y equals 1 to y equals 2. Okay, log of square root x, so log of y. Okay, dx is now 2y dy. And now it's just parts again, right? Okay, it's just parts again, all right? So, and this here, we're getting an area under the curve, okay? We don't have to worry about like going back into the original units. Okay, so we're going to go ahead and do the same kind of thing for that log problem that we did. So we'll set u equal to y. Sorry, u is going to be equal to log of y here. And then du is 1 over y dy. Okay, dv is 2y dy. V is equal to y squared. Follow your path. u times v, so y squared log y, evaluated on the boundary, minus the integral of v du. Well, y squared divided by y is just y. Easy peasy, lemon squeezy, right? Y squared log y minus antiderivative of y is 1/2 y squared between 2 and 1. And again, no need to go back into the original variables because the variable change makes it easier. Okay? Let's write down what we would need. 2 squared log of 2 minus 1/2 of 2 squared. Okay, and then minus 1 squared log of 1 minus 1/2 times 1 squared. All right, well, log of 1 is 0, okay, because e to the 0 is 1. All right, so what do we have here? 4 log 2 minus 2 squared is 4, divided by 2 is 2, minus, well, log 1 is 0, minus is plus, plus a half, okay? We'll have 4 log 2, okay, negative 2 plus a half. Negative 2 is, what, 4 over 2, right? And then we'll have a minus 3 there. That's it. Or if you want to be a little cheeky here, log 16 minus 3 over. Both the same answer. Why? Because, that log power rule I said from before. First one is still just as good. Okay. So what did this demonstrate? This priming substitution. Okay, you could also cheese it with another variable substitution. There's also another way to attack this if you are extremely clever. Setting x equal e to the 2y definitely gets the job done. But I think this is probably the most straightforward way to do this. If you spotted the log property ahead of time, good on you. Okay, it's a very good idea to have those in your pocket as well. I thought we were done with volume. Remember when I said in that video, some problems we'll encounter again are like 1 or 2 in each homework set where we have to find these volumes, but before we couldn't already. Hey, I got a brand new tool in my tool belt now. It's the integration by parts branded wrench. Okay, we're gonna find the volume of the solid, okay, by rotating the sine curve. Okay, and these bounded regions. So let's draw on the axes here, like I did before. Okay, x equals pi. Okay, so x equals pi right here. Okay, sine is boundary here. Okay, so there's our magenta area. As usual, you see me do this a lot, right? We're rotating around the y-axis. Green color. But it doesn't say which method to use. Personally, I think shells is easier because, think about slicing this perpendicular. You got to find an inverse, and that's trickier integration by parts that I don't want to handle with right now. Free to do it. But let's try to use discs. Sorry. Shells. Let's use shells. So let's think about it. Okay, let's do a refresher on shells, okay? The volume for shells is 2 pi. Shell radius. Shell height. All right, go back to that video if you need a refresher, but how did we do it, right? Shell radius, right minus left. Distance from the strip to the axis of rotation, okay? The radius here, x minus 0, okay? The strip is at a variable position x, rotating around the fixed y-axis, which is x equals 0. And the shell height, well, folks, it's just top minus bottom, right? Shell height is sine of x. We're integrating from 0 to pi, and so we have our integral to set up here. So let's go do it, right? 2 pi times the integral from 0 to pi. All right, shell radius is x, height is sine x. The x and parts. We use parts, all right? Let's just attack this with the DI method, shall we? Okay, I'll remind you again that D is going to be your U stuff, I is your dV. So in this case, we'll choose dV from the Liotte principle, be the sine function. is x, right? Differentiate until it vanishes. Integrate as many times as you need. All right. Tic-tac-toe, right? Check those signs. So what does this amount to? We'll have 2 pi times negative x cosine of x. And then minus times minus is plus there, so we have a plus sine x. Okay, pi and 0. Okay, definitely use your calculator for this, okay, if you need to. No shame in that. Okay, but there's going to be a lot of excellent cancellation here. Okay, I'm going to go ahead and just defer to my calculator here. But when you write it all down first, okay, everything works out very, very nicely. Okay, all that stuff on the inside just comes out to be pi. The volume is 2 pi squared. That's something, right? Okay, all this, type it in right, but be sure to write it down first, okay? I think we're slowly getting comfortable. Okay, you've heard me say it enough times to write before you type. So I'm gonna at times I'll go ahead and suppress this. Also, this video is getting kind of too long. But hey, 2 pi squared, a nice number, right? All right. Last one. Okay, we have an exponential here in blue. Y equals e to the minus x, which I just realized I graphed backwards. So because I'm not going to go ahead and do this again, let's go ahead and change the color here. Uh, make this red, say. Okay, something like that. Okay, so y equals e to the minus x. Okay, y equals 0 is the x-axis there. Okay, x equals minus 1. Okay, and then x equals 0. Around the line, x equals 1. Okay, so the line we're rotating around is there, and the region that we want is this here. Go ahead and color it in fully so we're trying not to be confused. I should have double checked this. I'm sorry, kids. All right. So we have that region, and this is again, shell seems a little easier here because if I use disk, I set it up in 2 integrals. I don't want to do that. There's our little representative strip. And once again, we are thinking shell radius and shell height, okay? Shell radius again, okay? Okay, let's just say that we're using shells here again. So the shell radius is going to be the distance from the strip to the axis of rotation. We think right minus left here. It's 1 minus x here. Here, going around the line y equals 1. And we have a strip at any position x. Shell height, top minus bottom, e to the minus x. All right, so what's our volume? 2 pi times the integral from minus 1 to 0, e to the minus x times 1 minus x dx. Multiply it out, yeah, one of those integrals is easy, and the other you'll have to use parts. But hey, you can use parts again for this one. Okay, di. Okay, again, black pen, red pen, excellent resource. Go ahead and subscribe. So we're going to set u equal to be 1 minus x here, and then dv is e to the minus x here. Watch the minus signs. Thankfully, integrating e to the minus x is easy. And then differentiating 1 minus x here, we have minus x. Sorry. You said be careful. Minus x, minus 1, 0. Tic-tac-toe, right? With the signs. So this integral here, okay, we have negative e to the minus x times 1 minus x, okay? Plus times minus is minus. And then minus times minus is plus, so we have plus e to the minus x. Okay, evaluated between 0 and minus 1. Okay, once again, defer to the calculator here. Okay, set this up and do it right. Okay, I think you'll get it. Not too bad. Okay. Turns out that all this in here turns out to be in parentheses. That's all E. So our volume that we are sought after is 2 pi E. And we're done. Folks, this was a long one, okay? But something to keep in mind, okay? That integration by parts is powerful. It is powerful, and it does take practice to spot when to use it, okay? Like with USub, Studios patterns. Okay? Practice. Practice doesn't make perfect, it makes permanent, okay? It's okay to be wrong, and it's okay to make mistakes. Okay, we'll do another integration technique in the next video. You gotta remember some trig formulas. I'll see you in the next one.